of this best paper session. So this second talk is called a two-sided matching model for data stream processing in the cloud fog continuum. This paper was submitted by Narges Mehran, Dragi Kimovsky, and Radu Prodan from Austria. So the speaker today will be Narges. Narges is a PhD student in the Institute of Information Technology, University of Klagenfurt in Austria. She's currently a research assistant in the Data Cloud project from the European H 2020 Research and Innovation Program. And Narges works on cloud, fog, and edge computing and data processing. So Narges, now it's your turn to speak. You can share your screen for your slides, and you have around 15 to 20 minutes for this talk. And for the audience, please send your questions to Narges through the Zoom chat. Narges, the mic is yours.
Thank you. Hello, everyone. Thanks for attending this presentation. Please let me share my screen with you. So, thank you. Thanks for the introduction, Lawrence. So, today I'm going to present for you our recent accepted paper in the CCGRI 2021 conference with the title of a two-sided matching model for data stream processing in the cloud fog continuum. My co-authors are Dragi Kimovsky and Radu Prodan from University of Klagenfurt. In this presentation, firstly, I will give you an introduction and then the motivation of our work. Then I will talk about the proposed model with the name of CODA, and then I will bring an example for that on that for you. And then I will present the evaluation setup, the results, and then at the end I will conclude this presentation. The digital world around us is witnessing an exponential growth in the amount of data that is being generated in the presence of the internet connectivity. Latency sensitive and bandwidth intensive data stream processing services such as the live video processing or social media based applications or IoT based applications are amongst the dominating traffic generators in today's world. But processing such a data stream in nearly real time for the end users of this type of applications required a vast and an enormous amount of compute, storage, and network services to be placed in the proximity of the data sources. That's why the idea of fog computing has been proposed by considering to place some sort of micro data center or femto data center which are directly connected to the base stations to do some pre-processing and to do some filtering on the data to be processed by the applications, the corresponding applications, before sending this type of data to the cloud data centers. Also, it has been proposed that some routers that are in the core of the network could be managed by the users of the application, and they will be able to allocate some virtual machines to their users to be managed by the users by considering some sort of open source frameworks, and they can be actually they will be able to process the data of the users. Also in some works, for example, in the research work and in one of the projects that our university is involved in, there has been this idea to consider a cluster of the single board computers such as the PI's devices or GPU-enabled NVIDIA devices to do some sort of lower performance ML training on the user's data instead of doing all of this ML training on the data in the cloud data centers. Therefore, it has been the motivation for our work to try to investigate such a heterogeneous cloud fog computing continuum in order to allocate its resources to the applications of the users to be deployed on such a computing and heterogeneous Continuum by considering that these sort of applications have some sort of strict latency, quality of service requirement, and also because of the enormous amount of data that this application needs to process, this type of application have the specific bandwidth requirement. Therefore, in this paper, we proposed CODA, which is the abbreviation of the Cloud Fog Data Stream Application Matching, in which we address the problem of the deploying such a data stream processing application on the heterogeneous computing resources by utilizing the matching theory principle. In this manner, we consider two sets of players. We can say that on one side, we have the microservices with the goal of lowering their completion time. And the other side, we have these computing resources whose goal is actually to lower traffic to be received and actually processed by the microservices which are going to be placed on them. So at the beginning, I will start with the application model. We have modeled each application considering this data stream type of application with the different number of microservices that they have. And you can see, for example, in this figure that there can be two different microservices, microservice U, which is the upstream microservice for the microservice MI, and then this microservice will generate and will flow some sort of data stream consisting of different number of elements towards its downstream microservice. Also, we have modeled two other microservices considering the source and the sink microservice, which are directly and respectively connected to the source of the data to receive the data and then to send it to other microservices. And then the microservice sink, which will be directly connected to the sink of the data, which will be actually the consumer of the data which has been processed by that application. On the other side, we have also modeled the resources considering a limited number of resources in the computing continuum. And for each resource, we modeled the CPU, memory, and storage of that specific resource. And also we defined another term, which is the which is the capacity of that resource, and it's related to the which is related to the utilization of that resource, whether that resource will be able to process, for example, more number of microservices and host more number of microservices or not. Also, from the other side, we had to consider, and we also had to model the network channels between each two microservices, consisting of based on the latency and the bandwidth requirements between each two resources. So for our model, based on these two application and resource models, firstly, we had ranked each side for the other side. I mean, for example, for the microservices, we have ranked the resources, and also for the resources, we have ranked the microservices. You can see each list actually next to each one of these microservices and resources. Then in the next step in our model, we have used such rankings in order to start to match the microservice from one side to the resources on the other side, in order to reach to really a stable matching between these two set of players. Let's see how we have did it actually. Firstly, I will talk about the ranking methods. For the ranking methods, we propose two different methods, and in the first method, it is on the microservice side, and we consider the microservice time, so that, for example, each microservice will rank the resource based on the microservice time, and then on the resource side, we rank the microservices based on the residual bandwidth that will be remained after being allocated to that specific microservice and hosting that microservice. So I will briefly actually explain each one of these two methods. For the microservice time, we calculated firstly the element processing time, considering that the data element that should be processed by a specific microservice being hosted by a resource consisting of two different components, the computation time and the transmission and the channel latency. And then at the end, based on the different number of elements that each data stream can have, we calculated the microservice time to be a method actually for the ranking on the service side. And then on the other side, we calculated the residual bandwidth based on the difference between the for example, at the specific snapshot of the system based on the difference of the available bandwidth and the amount of data that should be generated and being received by a specific resource hosting a specific microservice. We have then afterward, actually, we have defined the problem of the resource allocation as a matching game, in which, for example, on one side, we will have the generator of the data that should be received by a specific microservices. And then on the other side, we have this computing continuum, considering that they are connected in a specific network topology. Then our algorithm actually tries to find a suitable matching in order to match each one of these microservices to be hosted by the resources. I will bring an example for you in order to clarify how it works. Considering that, for example, as I previously mentioned, each microservice has previously ranked the resources so that our algorithm starts with the microservice, and each microservice such as M1 will look into its preference list and sees that, for example, here R1 is in the highest rank. Then R1 also will look into its preference list and sees that M1 has previously been ranked by R1. Then these two will be tentatively matched to each other. In the second step, actually, M2 also looks into its preference list and sees that R4 is in the highest rank. R4 also previously had ranked M2 in its preference list. So these two players also tentatively will be matched to each other. In the next step, M3, as the other microservice, also had considered R1 because of the lowest microservice time. Then R1 also looks into its preferences and sees that M3 is in the highest rank, and also R1 has enough capability in order to host more number of microservices. Then these two will be matched to each other. M4 has ranked R4 because of the lowest microservice time, and R4 has also ranked, although not the highest, but the lowest M4 in its preference list. So up to now, these two will be matched to each other. Let's see what happened in the next step. M5 will look into its preference list because R1 doesn't have enough utilization in order to host M5. Then it tries to be matched to R4. Then it proposed to R4. R4 looks into its preference list and says that M5 is ranked, but R4 actually doesn't have enough capability in terms of the CPU memory and other capability in order to host M5. But M5 has a higher rank than M4 that has been previously tentatively being matched to R4. Therefore, actually R4 rejects the matching to M4 and instead of that accept to be matched to M5. Then M4 at this step tries to take revenge and removes R4 from its preference list. R4 also does the same thing, and our M4 tries to be matched to another resource in order to complete the execution of the application. So it will be it tries to be matched to R1, but R1 also doesn't have enough capability. So they also take revenge and they remove each other from their preference list. So M4 at this moment just have one option and it should be matched to R3. As you can see, also because of the stable matching, we have to remove the other microservice also from the list of R1, as you can see, so that in the next step, RM4 is trying to be matched to R3. R3 has also previously ranked M4, and because its other choices have been already matched to other resources, so it accepts to be matched to M4. At the end, because none of the players in this game, in this matching game, will prefer any other choices than their current matched choices, so that we can call such a matching and a stable resource allocation of the microservice to the resources on the other side. For the evaluation, first let me to explain about the use case that we have prepared. This use case is related to the video stream type of applications, and it tries to get a specific video captured by some cameras on the roadside, and then actually it will try to encode the video based on, for example, a software tool such as FFmpeg, and then we utilize the OpenCV to actually put the video into different frames, and then we utilize the ML and inference models in order to exactly consider, for example, this traffic sign, what is the template of the traffic signs, and then also for transcoding and packaging, we utilize the FFmpeg software framework. And then at the end, the driver of the car will receive, for example, an alarm that this broken traffic sign is 20 kilometers per hour, and he or she will receive a warning for that. For the experimental setup, let me explain that we have considered both the simulation evaluation, and we did the simulation in the IFACSIM simulator, and also we considered the test bed, for which actually we had this Corinthian, and we designed this Corinthian computing continuum. For that, you can refer, and I would like to ask you to refer to this website. It consists of different level of the resources, from the cloud, fog resources, which are resided in the Vienna and also in Klagenfurt, and at the end they will be connected to the lowest level of the fog resources, which are interconnected through an open flow switch, and then inside that we have the single board computers such as the NVIDIA Jetson Nano devices and the Raspberry Pi devices. For evaluating the methods, actually, we designed two different metrics. One of them is the stream processing time, for which we consider the completion time of the last microservice, and also we consider the total streaming traffic based on the total and based on the aggregation of the data that will be passed through the network channels between the resources. We compared our work with the three state-of-the-art. One of them is the cloud approach, and then the two others are the combination of the resource allocation of the cloud and fog. For the simulation scenario, we consider two different scenarios. In one of them, we change and modify the CPU load by bounding the data size, and then in the second scenario we change the data size by considering that the CPU load was fixed. The result can be seen actually and can be observed in this figure. For the stream processing time, as you can see, by increasing both the CPU requirement and data element size, the methods were actually getting changed, and then we had an increasing result in actually by implementing different methods. Although for the stream, actually total streaming traffic, by changing the CPU requirement, we didn't have so many changes, because actually the data size was somehow fixed. Although in the scenario that the data element was getting modified, we had some sort of reduction in the total streaming traffic, because in a specific simulation time, the amount of data that were getting produced and generated was somehow fixed. That's why by increasing the data element size, the simulation was getting finished earlier. Let me talk about the scenarios that we had in the real testbed scenario. So we considered also the same scenarios that we had in the simulation, and we try to emulate those scenarios. For the modification of the CPU load, we consider different encoding bit rates by fixing the data size based on the frame size of the video. And then in the second scenario, we change and we modified the data size while fixing the bitrate of the encoding video. For in the both scenarios, we could have actually we reached the improvement almost up to 45% in comparison to the state of the art in terms of the stream processing time, and in the total streaming traffic, because of considering somehow one type of application. Actually the method, especially the three methods, didn't have that much difference from each other, although in the scenario that the frame size was getting changed, the total streaming traffic was getting increased. Okay, at the end, I would like to say that in this presentation, I talked about our proposal, which was CODA, and it was a method for running the stream processing application on the cloud and fog resources. For that, we considered the goal of lowering the stream processing time, and on the resource side, the streaming traffic, and we achieved up to 45% lower stream processing time and up to 20% lower streaming traffic. In the future, we plan to investigate the scheduling algorithm also based on the matching theory principles, and we want to investigate more the dynamicity of the user's application by considering that the resources in the computing continuum will be somehow, maybe, for example, they will have some sort of failure. So at that moment, what decision should be made. So these are somehow the references, a part of the references for our work. And at the end, I would like to thank you for your attention, and I would like to ask you to visit the websites for the projects. One of them is a data cloud project, which is the European project, and in which the role of, for example, the University of Klagenfurt is to design a scheduling method to actually schedule and deploy the big data pipeline on the computing environment. Thank you.
Thank you, Narges, for this very nice talk and perfectly on time. So I have a few questions that were sent on the chat.
Yes,
so
please.
First question from Muhammad Zakaria.
Yes.
Sorry, on your proposed model, it is essential to divide the application into different modules running on cloud, fog, and edge nodes. How applications are divided into modules, and is it possible to divide all applications into modules?
The type of the application that we considered was somehow the microservice type of application, so that they can be later on, for example, to be containerized, and then we can deploy each module on different resource, so that somehow it's not such as the previous type of applications, which were more monolithic applications, but it was more on the microservice based and component based applications, I should say. And we assume that, for example, the user has somehow designed such an application in previous, actually in advance, and then he wants to, for example, deploy such type of application on the computing resources, so that based on the requirement of each element of each component or microservice, then our method will decide how to deploy that. So this is somehow an assumption actually for our work.
Thanks. There is a question from Carlos. So Carlos, maybe you can ask it directly because we see you, so it will be nicer.
Sure, I can do that. So this is on slide 25.
Yes.
And my question is whether the algorithm that you're using there is distributed or decentralized, or is it decentralized or is it centralized somehow? Because you presented it in a very sequential form, but this can be distributed resources, right? So maybe some
yes, exactly.
consensus, or what properties does it have? Does it terminate? Does it have any fairness properties or load balancing properties?
So actually, the idea is that because of each one of, for example, we can call, for example, the microservice player or the resource player should be able to run this algorithm. Firstly, they should be able to rank the other sides by considering their own requirements, so that somehow they should act rationally and they do not have any idea, for example, what the other component, for example, microservice 1 does not have any idea what is the requirement of microservice 2, so that in this manner, I would like to say that, yeah, it can be decentralized decentralized implemented. And at the end, based on, for example, this ranking that each one of these player would have, then the matching, which is the main part of the algorithm, should be we should say that it will be somehow centralized, being implemented, and then decides that who will be matched to actually whom on the other side. I'm not sure if it was clear or not, so let me know if you want further clarification.
Yeah, so no, I think that is clear. So you will be, I guess what I understood, you will be needing some kind of central coordination at the end to make sure that you have the matching.
Yes,
that you
exactly.
want. And in this case, for example, your R2 and your R4, I mean, you could have had a matching where R2 is actually doing something. So I don't know about load balancing, whether, you know, I mean, in this particular example you have in there, R2 didn't have anything, but R4 got M2 and M5. Whereas you could have had R2 maybe have M2 or M5. So in general, what kind of, have you thought about what load balancing properties or fairness properties you may end up with in a decentralized kind of setting?
Yeah, exactly. So basically, we consider the utilization of that specific resource, and then we try to, for example, not to overload one specific resource while there are enough resources, so that it will be, for example, the decision of the orchestrator to check whether that resource is, for example, overutilized or not. And if it is not, so that the microservice will be hosted on that specific resource. That's why we designed a parameter which was the capacity, based on which the orchestrator can decide, for example, whether to allocate it, whether to overload it or no, if there are enough resources, so that it can be distributed and that other resource can do the execution.
Right. Yeah. Thank you. Thank you. I just wanted you to be mindful that when you have distributed coordination, you may end up with non-determinism, right? So depending on the order of things, you may end up with different results.
I see. Yeah. Thank you.
Okay, thank you. So I have received a lot of other questions. So stop sending questions. So it's okay for the audience. So one question from Maximilian. Maximilian congratulates you for your talk, Narges. And the question is, does CODA consider combinatorial optimizations like the Kuhn-Mungres minimal matching, KMM, or another common LP algorithm?
At the moment, what we considered was somehow, for example, based on this microservice time and then the residual bandwidth, we try to reach to, for example, each side will try to minimize its requirement, for example, whether it is a microservice time, so that it will target to consider that resource which has a lower microservice time. We did not implement any optimization-based algorithm, although, for example, on each side it can be considered, and then, for example, it can be implemented and deployed on each player, and then based on that, after this ranking has been set and has been formed, then the matching can be done. But we didn't consider it at the moment because we didn't want to overload the algorithm by, for example, considering different parts and different implementations and different algorithms for that.
Okay, perfect. One question from Tommaso from Pisa in Italy. In a real cloud application, you will have a high variability of processing times due to heterogeneous requests being submitted very dynamically. So processing times or data size would hardly be known upfront. How do you handle that?
I'm not sure if I could get the question.
So it's difficult to know in advance or to presuppose the processing times or data size. How do you handle that?
So that's why actually we tried to consider, and we try to, for example, consider the element processing time. Firstly, we divide the data stream into different number of elements, and based on each element, we try to guess, for example, whether this microservice, while receiving this data element, will be able to process that sort of, for example, application or not. I would like to say that, yeah, at the beginning somehow we would like to consider such a data streams that that a specific microservice, for example, here the compression microservice will receive a large amount of, for example, video data in terms of, for example, the frame size, and it will start its processing, so that at the beginning, somehow it will be clear for us, I would like to say.
Okay, thank you. 3 more questions. One question from Daniel Balouek-Tomer from Rutgers University in USA. How do you avoid NP-hard searches when performing the matching ranking model? Have you observed prohibitive overheads?
For that, actually, we didn't observe that much overhead, and our algorithm, for example, I am doing some tests for the extension of the algorithm. It didn't have that much overhead, and even, for example, for large cases, we could reach lower than 1 second to the matching of the cases. And at the beginning, this ranking methods really help in order to reach to a, for example, fair number of tests and cases that should be considered in order to match each side to the other side.
Perfect. And 2 last questions. One question from Yui Ma. How is this problem different from workflow scheduling in multi-cloud?
Actually, this was the resource allocation, and we didn't propose any, for example, at which a specific time the application microservice should start its execution. So what we assumed was that we allocate the microservice, and this microservice, for example, considering the container, will start its execution, and then it will receive the data in order to continue its execution. But I would like to say that based on this specific feature that such a new type of, for example, a software architecture have, it would be a little bit different from the workflow scheduling, although I guess that this algorithm can be extended in order to propose also the workflow scheduling. That's why now we are also investigating such a problem, because this big data workflow is somehow going to be considered a really large set of application components, and then we want to investigate in by which plan actually the component of such application should start their execution and should be scheduled on the resources of the computing continuum.
Thank you. And one last question from Asif Asnain, who congratulates you for the nice presentation.
Thank you.
How the model is trained with machine learning and how the hyperparameters were selected?
The model, actually no, but for example, for the use case application that we wanted to test our method with the other methods, yeah, inside that we consider some sort of components or microservices that were doing some machine learning training and inference. But at the moment, if we didn't actually interfere any ML-based model inside to that, or I don't know, any optimization based algorithm, because purely we wanted to test this matching game and then to solve the problem of the resource allocation specifically based on this matching.
Thank you, Narges, and thank you for replying to all these questions.
You're
so
welcome.
this is the official moment. So Young, maybe you can switch on your camera. I would like to share. Yes. Okay.
Maybe I should stop sharing.
Yeah, maybe you should stop sharing. Yes, maybe, because I cannot. Yes, thank you. So maybe Yang, you can officially give the best paper prize. Yang, please. Oh, I don't hear you. Okay. No, I should do it? Okay. There is a microphone problem. So this is the official moment. So Narges and Draghi and Radu, co-authors of the paper Two-Sided Matching Model for Data Stream Processing in the Cloud for Continuum, you officially receive the Best Paper Award, second prize for the conference CC Grid 2021, and congratulations.
Thank you.
So this is a virtual plaque. You will receive officially the real plaque through postal service, and you also receive a money prize of $500 that you have to share with your co-authors. You will have to decide how to share that.
Thank you.
This can be a nice negotiation. Thank you, Narges, and congratulations.
Thank you. I would like also to thank the anonymous reviewers and also the CC Grid committee for considering our paper to be awarded. Thank you.
Thanks a lot, Narges. It was very nice to select this paper.